Well, good morning, everybody. Good morning, John.
Morning.
So thank you, everybody, for joining us this morning for part one of our annual hydronics applications course. As you all are likely aware, COVID has forced us to take this virtual, but John and I are going to have a lot of fun doing it. My name is Michael. I'm the Technical Services Manager at Eden Energy. Eden Energy is actually a company that was founded in 1981. We have two professional engineers on staff, and our ethos is on providing good sound design assistance and providing packages to our customers. I want to take a quick second to thank the sponsors who've made this event possible. So we want to thank Flexcon, IBC Intergas, Water Furnace, Velo, Rayhow, and last but certainly not least, Calefi. This will be part one of four, where we'll be covering a variety of different topics. General housekeeping, there's actually 5 handouts that are available for everybody to download and take with them. The first one is actually Calefi's, one of their latest issues, maybe the last one, John, on air to water applications.
Yes, that's correct.
Perfect. So the other thing that is available is there's actually a Enbridge study that was just completed on heat pumps, in particular the water furnace heat pumps. It's a cooling report. And for next week's session, we'll actually have part 2, which is the heating report. It's a really interesting study. There's also a handout about improving the student experience through hydronics. There's a pretty interesting commercial study that was supplied to us about a new commercial installation that happened out west with some boilers. And last, but certainly not least, is actually a new manual that John wrote, which is a really good manual on buffer tank applications. So with that in mind, John, I'm going to hand it over to you.
Yeah, well, thanks, Mike. And again, I want to thank our sponsors. This has been a challenging year in a lot of respects, and Eden is so well known for doing much in terms of hydronics education, and we put this as a way to still reach out to folks and get some good information across, even though we can't do it face to face. So the first part of our 4-part mini series, as I've been calling it, is anatomy of a low temperature hydronic system. And you're looking at a schematic here, an overall schematic of that system. And you're probably thinking, how in the world does the water know where to go in a system like that? You'll see there's a lot of different components. This is a unique system. And the reason we want to talk about this system is it employs a lot of very state-of-the-art subsystems for heating, for cooling, and also for heating domestic water. And I just want to take you through it, show you the building, and show you how we implemented this. And you'll see I have some pretty close personal ties on this because the clients here, Andy, Heidi, and their son, Henry. Heidi's my daughter, and this house was built not far from where I live in upstate New York. So we had fun designing the house and also designing the heating system. So here's a quick look at the house. This was actually last fall. The deck wasn't quite finished off at that point. It's a modest house, a very well insulated house. You'll see there's some solar on the roof, which ties in really well with the heat pump. And again, the system that we're going to take apart today provides the space heating, the cooling, and also domestic water for this house. So the overall system, I'll just stay on this slide for a minute, just walk you around it very quickly. Over on the left side, you'll see there's actually 2 heat pumps involved in this system. There's a geothermal water-to-water heat pump, which is a 2-speed nominal 4-ton machine. And we also use this project as a test bed for a low ambient air-to-water heat pump. And this one was from SpacePack. So both heat pumps can operate if necessary. They can operate at the same time or they can operate individually. They're actually set up on a staged controller. And I'll show you some of the slides on that where we can set either heat pump to be the lead heat source. And basically they add heat to this buffer tank. that you see down here. This is one of the FlexCon Argosy tanks. It's a 119-gallon, very well insulated tank. And then over on the right side are all the loads. We're actually going to talk about this detail next week, but we've got some garage heating here. We've got basement floor heating. And then we've got up here in the upper right corner, we've got a mixture of panel radiators and radiant floor circuits tied into a manifold. Okay, so that's the overall system. There's a picture of the air to water heat pump, at least the outdoor portion of it. This is a split system heat pump. So there's refrigeration lines that go inside to an indoor unit. The indoor unit, if you've never seen one, it's roughly the size of a small ModCon boiler. Okay, and then down here, and in the photograph, this is the water to water heat pump. This is a 2-speed unit, 4 tons on high speed, and about 3 tons, actually about 2.5 tons on low speed. That worked out really well because our design cooling load is significantly smaller than our design heating load, and we don't want to be oversized in cooling. And just a quick shot, I'll show you several more job site photos. This is, well, let's see, this is myself, my son-in-law, and a good friend of mine unrolling 1,000-foot coils of 1-inch high-density polyethylene piping in a horizontal earth loop. We did some things there that are a little different from standard practice, but they've worked out very well. We'll talk about those details. So what were the design considerations here? Well, obviously we start off with the client wants, and my son-in-law in particular was really wanting to put a geothermal heat pump in his project. And I said, no problem. We've got a 2.5-acre lot. We had plenty of space to do a horizontal earth loop, and we had the availability of a large excavator nearby to put that in. So that was definitely part of the planning from the beginning. They wanted very simple controls, so we just put in what we call a master switch. In the center position, the whole system is off. Flip the switch one way, we're in heating mode. Flip the switch the other way, we're in cooling mode. Now, we use panel radiators because some of the flooring that they decided to use was not really conducive to floor heating. They had a fairly thick carpet and pad in the bedrooms, and then they had hardwood flooring with a thick area rug in the living room. And those of you that have done floor heating know that when we add layers of carpet and padding and so forth, we build up a lot of R value over our heat transfer surface, and we don't get much output from it. So to accommodate what they wanted to use for floor coverings, we decided let's use panel radiators in those areas, and let's keep it simple. Let's tie it all together with the same water temperature. So we actually sized the panel radiators. We sized for design output at 120-degree supply water temperature. And interestingly, we found that we can actually run this system at about, on a design day, at about 110-degree Fahrenheit water temperature. For cooling, we used a single central chill water air handler, a 3-ton air handler. It's actually mounted up within the thermal envelope up in the heated attic space, and just a standard duct system to deliver that. And we operate that as a single zone. And then they also wanted to have a small wood stove for backup if we do get power outages that can last a day or two if we get an ice storm. So we are out in a rural area. So we put a small wood stove in, so you'll see that there's a chimney for that. We do have a thermostat, a single thermostat in the house. Well, I shouldn't say that. We have a single thermostat in the main living area that controls the heat output to the, we'll call it a great room area. It's a combination of a kitchen, a dining room, and a living room. And then on the individual panel radiators, we went with non-electric thermostatic radiator valves. And again, you'll see some photos of all these coming up. Now again, floor coverings. In the kitchen, we had a engineered wood floor, which was suitable for floor heating, relatively thin, glued down to the subfloor. Okay. We also used that same flooring in the living room, but we had they wanted to use a thick area rug over it. So You see in red there, the R value was deemed to be too high for floor heating. Bathrooms were ceramic tile, no problem. We're going to use floor heating there. And the bedrooms, again, carpet and padding, R value is too high. So if you look at these, what the client wanted to have and also what our constraints were in terms of flooring, we got a lot of constraints here. But one of the beauties of hydronics is that we can design around these constraints. We've got a wide spectrum of hardware and design techniques, and this system really represents an assembly of those different design concepts. So here are the drawings of the house. We worked on this. I have done housing design years ago. I kind of got out of that to focus more on hydronics, but I guess you'd say this is architecture from an engineer's standpoint. It's a pretty basic house. It's designed to go together quickly. This uses I-joists for floor framings that go in fast. It uses 24-inch on-center framing, which also goes up fast, uses less wood, better R value in the wall, and then it uses trusses on the roof. So the structure of this house and the geometry of this house lent itself to fairly rapid construction. It is on a slightly sloping lot, so when you look at the south elevation down here, you see that it does have a walkout basement, and we put a fair amount of glass on that south side so we could get some good solar gains in the wintertime. And this house does face directly south, so the roof surface was a good mounting platform for some solar PV panels, which again ties in really nicely with essentially all electric heating system. So here's photos. Again, these were taken last fall, just when we started to get some snow. I think these are probably early December photos. And if you look at the north elevation here, you can actually see the outside portion of the air-to-water heat pump right here. And then on the south elevation, here's this is a just under 8 kilowatts peak rated solar PV system. These are each of these panels, these solar panels, has a micro inverter, and each of these reports to a website. So we can pull up a website at any given time and find out exactly what the output of each of those panels is, how much energy the system has produced over a day, over a month. It's a very, very nice system. So let me start up here with our list. We have about 3,300 square feet of finished space in this house. And I listed the R values here. It's a fairly well insulated house, not quite up to what some of you may know as passive house standards, but R29 walls, above grade. The basement walls were R24. The roof was R51, used a combination of spray foam and mineral wool bats. And then all the windows in the house are a triple glass low E coating, R3.8. So when you mix that space size with those R values, our design heating load, which is at minus 10 degrees Fahrenheit, so it's cold. We're at almost an 8,000 degree day climate here. 35,000 BTUs per hour, excluding the garage. Now we can heat the garage. I'll show you the slab does have tubing in it, but we don't maintain the garage normally, simply from the standpoint of saving money. We can turn that on. That is on a separate antifreeze-based circuit. So when we turn the garage off, it can go below freezing without damaging anything out there. So if we look at our design load and the amount of finished floor space we have, we're just over, I should say, just under 11 BTUs per hour per square foot. So this is representative of modern construction. This is relatively low load. Compared to houses perhaps 30 to 40 years ago, they would probably be close to about triple that amount, maybe around 30 BTUs per hour per square foot for design load. We talked about the PV system. Essentially, the idea here was to go with an all-electric house with the exception of the small wood stove. And you see, here's the chimney for the small wood stove right here. And that was put in essentially as a backup to a power outage situation. They do have a small standby generator, but it's not quite large enough to run the heat pumps and the other appliances in the house. So the idea was the wood stove is there for backup and for a little bit of ambience. And we have a lot of wood around, so there's no problem coming up with the firewood for it. Now, regarding mechanicals, here's the floor tubing layout for the basement. Start over here on the right. It's a pretty simple layout. You'll see individual circuits. This is all 1/2-inch tubing. And we laid this out starting from a manifold that is in the corner of the mechanical room. This area down here on the north central area of the basement is our mechanical room. So the manifold is located here, and you can see our circuits go out. You might be wondering, what's the deal with these out here? Well, a little hard to see it, but my son-in-law and daughter said, well, eventually we might want to partition off this basement. Right now, this is a big open space, which is really nice. But if they do want to partition that off, we set up the tubing circuit so where the partitions would go, if there was any mechanical fasteners going into the floor, we're not going to be over an area that has tubing in it. And we could potentially adjust the flow rate in those circuits or put manifold valve actuators on those circuits if we wanted to have room-by-room control. We do have one other area here, kind of we'll call it the cold storage area. This doesn't have any tubing in it. There's a breezeway that's 12 feet wide that connects the house to the garage. And you'll see we tightened up our tube spacing. Here we have 6-inch on center tubing. The reason we did that, there's a fairly high ratio of exposed wall to floor area here. And this is also an area where people come in the wintertime, or if it's raining out, the floor is going to get wet. There inevitably is going to be snow and water on that floor. So we wanted to have a little higher heat flux there just to keep that dry. And then we put a separate manifold in out here for the garage, and just 3 circuits, 1/2-inch tubing. You can see we worked around the floor drains. The black dashes that you see here, these are control joints. These are locations of saw cuts in the slab, and we sleeve the joints. So if there's any slight movement in the slab at that point, we're not putting direct stress on the tubing. And let's see, I think we talked about most of this. Our basement circuits, even at design load, the average water temperature is 98 degrees. Again, we've got 2 inches of foam insulation all the way around our concrete walls here, and then there's a 2x4 wall that has a 3.5-inch mineral wool bat in it. And the actual structural wall is an 8-inch reinforced poured concrete wall. So a pretty straightforward layout here for the tubing. You can see all our circuits are identified with a length. So we know when we draw this, we use the CAD system, measure the length. We know that we're establishing reasonable lengths for our tubing circuits. And we also know how much tubing to order. So here's some photos of that tubing going down. My good friend Harvey Euchre, a longtime hydronics contractor. I call him a hydronics artisan. He does beautiful work. One of the things he likes to do, he'll take the tubing plan and he'll go in there with a few cans of colored spray paint. And you can see here, he's kind of laid out where the tubing's going to go. And of course, he's doing that before the tubing goes down. So, you know, if it take an hour or two to take a tubing plan and some spray paint, you don't have to spray paint the entire circuit. You can see, for example, here, he's just spray painted where the return bends are going to be. This really helps when it's time to pull the tubing off the coil and fasten it down, and save a lot of time in the field by doing a tubing plan and doing a layout. We set up the manifold station here, just a couple pieces of rebar down through the foam and a piece of plywood as a board to hold that manifold. This is the tubing out in the breezeway. You can see our 6-inch on center spacing here. We have to widen out our tubing bends a little bit so we don't kink any tubing at that point. And actually all that tubing goes back through a 2-inch PVC sleeve that actually goes back through the poured concrete wall and brings our tubing into the basement where we can extend it over to the mechanical room. This is the morning of the pour right here. Concrete crew setting up, they actually took a piece, I think that's a 12-inch piece of PVC pipe, and they use that as their chute extender. and they were able to back right up close to the wall with the truck and run all that right down through the chute. So the entire basement has 2 inches of foam insulation under the slab. The only exception, it's a little hard to see it, but the only exception is where there's some bearing footings here. We have a center bearing wall, so there's actually no foam right here, and the concrete slab would be thickened at that area, and there's another area over here. You can see there's 2 inches of foam here along the entire wall as well. And the basement portion of the system's simple. It's a 3-way motorized mixing valve that operates based on outdoor reset control. It's a small ECM circulator that's running at a constant speed. We aren't modulating our flow rate into the basement. At least at this point, there's no need to do that. And then a manifold with the 5 circuits on it with its own thermostat. And this piping leads back. And again, you'll see how that ties into the overall system. Here's our outdoor reset curve. So at -10, actually I'm showing about 90-degree water on this graph right here. This is just a combination of a lot of insulation, and most of our tube spacing in that basement is 12 inches on center, right out near the exposed wall. You can see over here, we're at 6 inches on center in roughly about 3 feet, just to get a little higher output where our losses are higher. And if you look close, you can see we do have 2 inches of foam all along that perimeter wall. We actually tapered the upper side of that foam at a 45-degree angle. And that's so when the concrete is poured, it'll actually come right up to, or come very close to the 6-inch wide wall at that point. So by the time you put the 2x6 wall, the drywall, and the base molding on, there's not going to be any foam showing. So these are small details. You can actually see them right here too. Some tapered foam on that side, a little bit over on that side, and pretty straightforward. Now let's move up a floor. This is the main living level of the house. Over here on the left, this is the great room, the kitchen, the dining area, and the living room. Again, the living room, you don't see any floor heating there because that's where the big area rug is going to be. So here's a couple of 48-inch wide, 24-inch tall panel radiators. The kitchen area where we had just an engineered hardwood floor, that is 8-inch on-center tube spacing, and that uses aluminum plates over the tubing. These are 5-inch wide, 24-inch long aluminum plates. And these center lines that you see here, these thin black lines, these are the center lines of the floor joists. So when I made this drawing to show the tubing layout, we always like to locate our framing because obviously we've got to put our tubing and our plates in between that framing. And we worked it out so we had 8 inches on center coordinated with 24-inch on center framing. There's a couple circuits here. They come back to the mechanical room, and actually they eventually tie to a manifold. It doesn't show it, but the manifold's over in this area right here. The other 2 floor circuits, there's the master bathroom. So this was kind of, I'll be honest with you, this is kind of a tedious layout right here because these are very short runs just because of the geometry of the room. But they did go in. We did put the aluminum plates on, and 8 inches on center. We have another run that goes over here. This is the second bathroom on the main level. That's ceramic tile flooring. One thing I didn't point out, if I go back to the kitchen, we did not install any plates under the kitchen island. And the idea there is, well, we've got cabinetry, an island above the floor. They don't plan to store food there, but who knows? Over time, somebody might eventually store some food there. And we don't want to heat up any cabinets that might have food stored in it. It's just going to cause, premature spoilage of the food. So instead of trying to route all the tubing around it, we simply didn't put any plates on. So there might be a trickle of heat there, but it's really without the plates on it and the tubing not stapled up tight to the floor, it's really going to be minimal transfer. And I'll wrap this up. The other panel radiators that you see are in the 3 bedrooms. Here's a 36-inch by 24 high panel rad. 48-inch by 24 panel rad here. And then the master bedroom's a little bit larger. There's a couple windows there. That has a 63-inch long panel rad. Now, these radiators might look a little large for these rooms, but remember, we aimed at design load on a very low water temperature, so we have good compatibility with the heat pump. And right now, as I say, we're running at design load, we're running about 110-degree water. And these 3 panel radiators all have thermostatic valves. And to coordinate the thermostatic valve approach, we also set up valves for the floor heating in the 2 bathrooms to use these thermostatic radiator valves. And I'll show you a picture of that. Remember, thermostatic radiator valves, many of you are used to seeing them on panel radiators, built right into the panel radiator. But you can also get these valves that have a capillary tube that leads off between the actual knob where you adjust the room temperature and where the valve is located. And that's what we used in the 2 bathrooms here. So we actually have 5 areas of heating that are being controlled by non-electric thermostatic valves. And then the 1 thermostat on this level does control these 2 radiators and these 2 floor heating circuits.
John, while you're going through this, we actually do have a question.
Okay.
It's just a general question on the master bedroom and the fact the radiator panel is where it's located.
Yep.
The question is not on the exterior wall. He's noting you have it on the interior wall and looking for you to comment on that.
Yep. Interesting. Good question and good observation. This was done because honestly, the bed and the 2 nightstands that went in there were huge, and we were not able to put that panel. I would have preferred the panel over here, but because of the furniture layout, there's just no way to do that. And with these R values in the wall, quite honestly, I don't perceive any comfort difference. So you can put a panel radiator on an interior wall. Normally, we like exterior walls if possible, but again, we looked at this. We actually put scale representations of the bed and the 2 nightstands and found there's just no good way to make that fit in that room with that radiator up in this area here. So.
Now, John, there was another question that came in that's a good one, and which is how well the transfer plates work. If you look at independent studies that are out there, Virginia Tech University in particular did a study looking at regular staple up, pegging it around 10 to 12 BTUs per square foot at 110 mean water. Putting transfer plates on that makes a significant increase. You can get easily, 17 BTUs per square foot at the same temperature. What are your thoughts on not using plates?
I don't like not using plates. We call it plateless staple up.
I call it the constipated heating system.
Well, thermally constipated heating is another way to look at it. Honestly, folks, you will not find this in any part of the world other than North America. And that should tell you something. The transfer plates, years ago, we set up some modeling where we used something called finite element analysis to study plated systems versus unplated systems, where everything's identical except on the 2 systems we're comparing, one system has the plates, the other system doesn't. We got a 3-to-1 output ratio. We got 3 times the heat output with the plates compared to the plateless system. So again, I'll stress, to get the best performance out of these heat pumps, we want the lowest possible water temperatures. And the way that you get to low water temperatures is designing efficient heat emitters. So putting those plates on in a system like this is a critical detail. 8 inches on center, the plates are on there, and also we used 6-inch fiberglass bats. And one of the other questions that I get, and this kind of goes back several years in the radiant industry, should you push the insulation right up against the bottom of the plates or leave an air gap? And actually ASHRAE did a study on this through Kansas State University several years ago, and they actually found better performance when the insulation was pushed up against the bottom of the aluminum plates. So just push the insulation up there. We use craft face bats, and we used a little tab on the craft facing just to staple the bat, hold it in place there. Okay. Now, this shows the other portion of that main floor system. This is the combination of panel radiators and the floor circuits we talked about. I'll start out in the living room. We had the 2 radiators, and actually we eliminated this 1 radiator in the dining room. Just again, because of space, it turned out we didn't need it. So we've got 2 panel rads here. These are 48-inch wide panel rads, and we got the 2 floor circuits. They all come back down to this manifold, and we have a thermostat on that, in that portion of the building, and that just controls the zone valve. So when that thermostat calls for heat, basically hot water or warm water flows up simultaneously to the 2 panel radiators in the living room and to the floor heating in the kitchen and the dining room. And also we tied the breezeway circuit in because oftentimes the door between the kitchen and the breezeway was actually left open. So even though it's a separate area in a sense, thermally it's essentially treated as part of the kitchen. Now, the other manifold has the 3 bedroom panel radiators, and you can see these are the thermostatic radiator valves. The master bathroom has a towel warming radiator and that floor heating, and we just put them in series. This is a short circuit, not a lot of head loss there, very little head loss through this towel warmer. So we basically route our warm water through the towel warmer first and then down through the floor. And we used a valve. This valve is actually mounted under the floor, but it's accessible from the basement. And there's a capillary tube that goes up to the TRV mounted on the wall. And that's what it looks like. Just a simple knob. It has numbers from 1 to 5. You just change the setting and it monitors the room temperature and controls the flow rate going through there, just like a radiator valve mounted to a radiator. And in the other bathroom, same control. This is the tubing where it pops up through the floor under the radiators. We used a dual isolation valve on all these radiators. So if we ever have to service a radiator, we just take a screwdriver and turn these 2 valves, close it off. You can, there's actually unions on the bottom of the radiator here. You can see them. But if you had to service that, we would take it apart right here. These are just little white plastic covers that snap over the tubing just to give it a clean appearance. And here's a finished panel rad in the living room right here. So you see the tubing comes right up through the bottom, right on the center line. These are Myson panels, what are called Myson T6 panels. And in the living room, there's no thermostatic valve mounted because, again, those panels are being controlled by the thermostat. This is one of the bedrooms. There's the TRV. This is that radiator in the master bedroom, 63 inches wide. And again, a TRV on that. You can see the carpet on the floor there. So one of the things I like about hydronics is the ability to customize a system. And this is very customized from the standpoint of aesthetics. It's customized from the standpoint of floor coverings, and it's in compliance with what the clients want to use as far as control options. There's other ways we could have done this. For example, we could have put an electronic thermostat in every room and put a bunch of valve actuators on the manifold, and I'm sure that would have worked. I'm sure it also would have been quite a bit more expensive, and quite honestly, I doubt that it would be used much. If you're going to do room by room temperature control, trying to justify that, with the exception of the TRVs, TRVs make it very easy to do room by room temperature control. But to do it with a bunch of thermostats, I would ask the client, how often do you anticipate adjusting those thermostats? Are you going to adjust them every day? You're going to have different set points, so forth. If the answer is, yeah, we're going to adjust them continuously, then maybe it's justified. But if you're just going to turn these thermostats to slightly different settings, like one room is 68, one room is 70, the other room 72, we can do that by balancing. We don't actually have to have a thermostat in every room to do that. So keeping it simple is another important aspect here. Before I leave this slide, you can see this is the towel warming radiator in the master bathroom. The wall got painted so we could put the radiator up, and they got to go back and do the trim paint in there. Okay.
So John,
Now,
John, if you can go back one slide, there was actually a good question that came in, and I'm sure others have. The question is, how are you controlling the operation of the boiler or an air-to-water unit when you're using TRVs?
Actually, the heat pumps turn on and off completely independent of the TRVs or this thermostat. The heat pumps turn on and off strictly based on the buffer tank temperature. So when we enable our system in heating mode, the buffer tank becomes the target for the heat pump operation. And that way our buffer tank is basically sitting there between an upper and a lower temperature range. And so whenever a TRV or a thermostat opens up, there's always a reserve of hot water to go out. It's a good question. It's a different control technique from where you would have, for example, several electrical thermostats going back to a zone relay panel and then perhaps fire the heat pump based on that. So completely separate between the heat pump operation and the zoning controls.
And John, would you do anything different? Would you do anything different in a boiler application with those TRVs?
You know, you could. It depends on how many. If you've got a lot of zones, I would always recommend a buffer tank anytime you have extensive zoning in a system. You could set up the the boiler to maintain the buffer tank. That's a reasonable way to do it. You're going to get reasonable boiler cycles. Without a buffer tank, you know, it's going to become, especially under part load conditions, it's really going to become a situation where we're trying to avoid short cycling the boiler, and a buffer tank goes a long ways towards eliminating those short cycles. So yeah, you could do the same thing with a boiler. Mike, is Lance McNevin standing by? I think we had a question at this point on PEX tubing.
We do. So Lance, can you hear us okay?
I sure can. Can you hear me?
We can. So throughout this presentation, we're going to be answering questions, and some of the participants emailed questions in. So Lance is the Director of Engineering for the Plastics Pipe Institute, and this question specifically has to do with PEX. So we're going to quickly interject now that we've done our PEX component. So Lance, in 2 minutes or less, good luck, it's a good question. If you could just answer the question that's been submitted. So Chris has asked, he's heard recently about the risk of pinholes developing in copper potable water recirculations, and he's concerned about hydronic tubing, specifically PEX, and whether there's concerns that PEX is going to have the same issue, whether it's used in concrete for radiant applications or as part of a recirc line. So Lance, why don't you take a shot at that for us?
All right, thanks. So good morning, everybody. And I've been a radiant guy since the early 90s, a student of John's for more than 25 years. So I appreciate being part of this today, and I always appreciate listening to John. The question seems to have a few different aspects to it, but if the question was about velocity, there's certainly no velocity concerns there. If we're talking about high velocity, continuous recirculation through PEX tubing, wearing it out over time, like could happen with copper. We know that copper is very sensitive to velocity with temperature, limited to 5 feet per second at any temperatures above 140 degrees Fahrenheit. PEX has no such limitations. Studies have been done with 12, 15 feet per second of velocity through PEX for millions of gallons of flow, and there's no change to the material. So there's no real upper limit in terms of a feet per second velocity limit for PEX. If the concern is about temperature degradation, as we're seeing here in John's drawings, we're using PEX to supply our high temperature radiators, which is a great idea. And all the PEX tubing that's for sale in North America should be certified to the CSA standard called B137.5. That's B as in Bob, 137.5. And that standard requires long-term testing on the PEX tubing before it's certified and allowed for sale. And the tubing is all rated for continuous operation of 100 PSI at 180 degrees. So I'm pretty sure the John system is not running at 100 PSI, even though it might be at 180 degrees. So that means the tubing has more than enough capacity to run for many, many decades of use at 180 degrees. And you're probably not heating the house 365 days a year anyway. So this tubing is all expected to last, 50 years or more at continuous operation. But we're not really running our heating systems every single day, I don't think. There's a lot of good information in the CSA standard called B214, B as in Bob 214, which is all about installation for hydronic heating systems, and that's actually the code in Canada. So many of the people on the call today probably are aware of that. And I'll just plug one other document if people want to read more about high temperature usage of PEX. There's a document at our website called Technical Note 52, that's TN52, and that talks about usage of PEX at temperatures even above 180, which wouldn't apply in a situation like this, but in some sort of commercial application, it could be needed to run the PEX above 180. So that PPI document TN52 addresses that.
Perfect, thank you, Lance. If
actually,
anybody has any follow-up on this, obviously we can help you with that. You can drop me an email or give me a call in the office. I've known Lance for many years, and he's a great advocate for the industry.
Yeah, and going back to this system, we're running a maximum water temperature here of 110 Fahrenheit, and we're at about 12 psi. So we're from a temperature and pressure standpoint, we're well below those limits that Lance talked about on the tubing. I want to make one last point before I leave this slide. I just wanted you to know we left one spare connection on this manifold and actually 3 spare connections on this manifold. We do that so that if at some point somebody wants to add another radiator or maybe a little fan coil, I don't anticipate that that'll happen here, but over the life of the system, you never know. Somebody might build an addition on this house. And if they do that and they want to add a radiator, by having spare connections on your manifold, you make it pretty easy. You can isolate that manifold. They don't show here, but they're shut-off valves. And we could shut off and very quickly run our PEX, pull our PEX tubing through the structure to whatever that new heat emitter is going to be, and then just tie it right in. So it's one of the things I like to do. It's a relatively small cost to add 1 or 2 spare connections. We just put a cap on there that's got a little plug with an O-ring that seals it off. And it's a sellable detail. If you're talking to clients with the idea of, if I ever want to expand this system, can I do it? Try to make it easy for them to do that. Now we're going to switch from our heating distribution system. We're going to take a more specific look at our geothermal heat pump system. So I'm breaking that part of the schematic out.
So John, let's take a quick break here and let's throw our poll in for everybody.
Okay.
The other thing I'll point out to everyone is that we are going to answer all of your questions. There's a ton of great questions. Towards the end, we'll answer everything. We'll keep interrupting with ones that really fit in well. So if everybody can take a second, you should see the poll right now. So we just want to know how many of your hydronic systems are geo. So hopefully you can see that. So we'll just give everybody a second to vote. Certainly for us as the water furnace distributor, we see quite a bit of our customers, John, using water-to-water heat pumps and geo.
Yeah, low temperature hydronics, water-to-water geo, great combination.
We'll just give it another second here. We got almost 70% of the people voting. This is clearly a very difficult trick question with a nice little typo in there too, John. So I'm going to close this poll, but we ended up with 52%. It's less than 25% of their business, and 35% actually said none. So I would say there's not a lot of water-to-water equipment happening with the people that are joining us today.
Yeah, but the future bodes well for heat pumps. So electricity is going to be pushed very heavily in North America Beneficial electrification is really the mantra that a lot of, I believe the Canadian government, I can certainly speak for in the United States, it's going to be a major push to move electrification in favor of fossil fuels. It may not complete in our lifetime, but I'll give you a quick example. In New York State, we are supposed to be 100% renewable electricity by 2040. That's the governor's decision, and there is something like $425 million slated in New York State to promote heat pumps. So, it doesn't really matter how you feel about that, whether you think that's the right thing or not. That is where the industry will be moved by the government and these incentives. So if you aren't doing heat pumps now and you want to stay into modern hydronics, I really encourage you to take a good look. And again, we're going to talk about both water-to-water geo, and we're going to talk about low ambient air-to-water heat pumps, both of which are a good tie-in with hydronics. So let's, we're going to kind of take this system, this subsystem apart. I'll start out in the dirt here. We've got 4 loops that are about 950 feet each. This is 1-inch SDR11 high-density polyethylene. I'll show you a cross-section of this in a minute, but it's a horizontal earth loop, and they come into an interior manifold. This is one of the things that is different. A more routine geothermal system would use either butt fusion or socket fusion outside and basically manifold multiple parallel circuits into a header and just bring 2 tubes into the basement. And that's okay. There's a lot of systems out there that have done that. We went with an interior manifold for a couple of reasons. One is we didn't use any joints outside the building. We used 1,000-foot coils of tubing. There was no need to go out and get any kind of fusion equipment. I don't own the fusion equipment, so that was one factor. The other factor, one of the things that's really nice about an interior manifold, it's a lot easier to blow the air out of it at startup because you can isolate 3 of the 4 circuits, focus your flush cart flow on one circuit at a time, blow the air out of it, and just like you would with a radiant manifold, you would work your way across the circuits, flushing them out individually. And I don't think we'll ever have a problem with this tubing outside, but if we do, and we can identify the circuit, we could isolate it. All these circuits have 1-inch ball valves that are inside. And again, I'll show you a photo coming up. So we have the ability to isolate any given circuit if we want to. I'm a big believer in expansion tanks in earth loops. Again, in North America, this is not necessarily a routine. You'll find it very commonly used in European geothermal systems. It's a closed loop, and it should have an expansion tank. Now some people will counter that. They will say, well, the plastic pipe will expand and contract, and that's true, but we actually found that the rate of expansion and contraction of the plastic pipe is different from the rate of expansion and contraction of the fluid. This is a 25% solution of propylene glycol in water. And the difference in those rates of expansion can cause fairly wide pressure fluctuations in the earth loop. You'll find the pressure will go up in the winter because the tubing actually shrinks faster than the fluid. That will cause the pressure in the loop to go up. And then the opposite occurs in the summer. The pipe expands faster in its internal volume compared to the volumetric expansion of the fluid. And that'll cause the pressure to go down, and it can go down to the point where the pump will cavitate. And I've seen that happen on some earth loop systems. So by putting in an expansion tank, you can minimize those pressure fluctuations in that loop. We also put an air dirt separator in there because, again, it is a closed hydronic circuit. We want to get the air out of it. We were very careful when we put the pipe in, and because we don't have outside joints in the pipe, we really should not have any dirt in the pipe, or very, very little. But just in the course of assembling things, a little bit of dirt might get in there. And we also use a high efficiency circulator here. This is a stainless steel volute ECM circulator. It runs on roughly half the wattage that a typical wet rotor circulator with a permanent split capacitor motor would run on. So that's the earth loop. The heat pump is a reversible heat pump. It does have a de-superheater for domestic water heating. And basically it pipes over to this 119-gallon FlexCon tank, which is a polypropylene inner tank. It has fiberglass reinforcing to give it its pressure rating. And then it has a monolithic urethane insulation shell around it. Really nice tank to work with. Now, just the photographs. This is the heat pump itself where the piping connects to it. Here's the buffer tank, and you'll notice we use 2-inch stainless steel T's to build our headers. One of the terms I like to use with headers is short and fat headers are good. So we want to keep the pressure drop in the headers very small. So in addition to thermal buffering, the buffer tank helps us with hydraulic separation of the circulators. So rather than get 2-inch copper and solder it together, we actually found it was less expensive to use the stainless steel T's. And these are just close threaded stainless nipples in here. Here's a bushing to adapt down to 1-inch pipe, and threaded those onto the tank. Actually supplied, I believe they're 4-inch long, 2-inch pipe size stainless steel nipples that supplied with that tank. So there's the upper header and then a lower header down here. We got a sensor well in the end of the T here, another sensor well in the tank. Now let's go on. Performance of the heat pump. This is pretty much the story with any current generation heat pump. The higher the condenser temperature, in other words, the higher the water temperature that the hydronic system requires, the lower the heating capacity and the lower the COP. So these are the performance curves here. Heating capacity is a function of the entering water temperature from the earth loop. This time of year, our entering water temperatures in this location are around 60 degrees, high 50s to 60 degrees. We actually peak out at that 6-foot depth at roughly this time of year. But by spring, with this heat pump operating, those loop temperatures will start to get down into the low 30s. So we've got a range here of loop temperature, and you can see the capacity of the heat pump will vary. You see a little bit of a difference here, a slight drop in performance when we go from 95-degree leaving water temperature to 110. But if you jump over to COP, you'll see there's a significant difference between the coefficient of performance at the higher water temperature versus the lower temperature. And again, both of those are functions of the entering temperature from the earth loop. So bottom line is, the lower we can keep that water temperature and still maintain comfort in the building, the better that heat pump's going to perform for us. Now here's the loop. Our local excavator, he's got a John Deere 210 with it's a 25-ton excavator with a 6-foot bucket on it. So we had no problem digging this trench. And when you look at this trench photo down here, it looks like the tubing isn't that deep, but we have OSHA requirements. And the OSHA requirement is if we're going below 4 feet, we've got to side dress that bank so we can't have a cave in. You don't want to get into a trench that has a 6-foot vertical wall in it in the ground. That can cave in and it can kill you. So you can actually see the finished grade is roughly about here and roughly about here. And our excavator is just digging out a bit so we have the safety. And basically we're just rolling out 1,000-foot coils of 1-inch polyethylene, high density polyethylene. We've got 4 pipes at the bottom of that trench. And then on the way back, excavator put in 2 feet of fill, and we brought our pipes back at the nominal 4-foot level. So, for example, this would be supply and return on one circuit, another circuit, so forth. So that's our trench. And the layout of this trench, because of other things like septic fields and trees and so forth on the site, we had to do kind of this arcing pattern. And here's the house. We came out of basically the northwest corner of the house, and you can see we curve around about 270 degrees. And when you lay the tubing out in a trench like that, obviously as you're coming out, the tube that's running along the outside of the trench is using up more length. than the tubing running on the inside radius of that trench. So by the time you get to the turnaround out here, you've laid down significantly more pipe on that outer circuit than you have on the inner circuit. And the solution that we used for that, actually our excavator suggested this, and it turned out really well, is we simply took the outgoing pipe at the 6-foot depth and we turned it around and we made it the inside radius on the way back. So what he did is he dug, here's our 6-foot excavation. He actually tapered this up and made a shelf up here at 4 feet. So we basically just brought our tubing up gently, no rapid turns or steep bends, tight bends in the tubing, and we just coiled them around, did a 180-degree turn and went back, and then he worked back, and actually he did a good job at this with this bucket. He could actually place the backfill onto that tubing. You got to be careful. You want to drop it straight down onto the tubing. You don't want it to be kicked in from the side because that'll push the tubing around. We did use some what are called landscape staples occasionally to keep that tubing where we wanted it. These are just little 2-inch wide, 6-inch long. I think they're 10 gauge steel. Just tap those into the ground just to secure it. And then on the way back, the excavator basically set it up so he could very gently place that backfill and not push that tubing around. So by the time we got back to the house, all our circuits were within about 2 feet length of each other. And we actually turned around a little sooner than we had to. We could have used up a little bit more tubing. We ended up with 4 circuits that are roughly about 950 feet long, starting with 4 1,000-foot coils. So that's our earth loop. Now, how do you get the earth loop into the building? Well, you could pour the wall and then go rent a core drill, a 3-inch core drill, and bore 8 holes, 3 inches in diameter through the wall, and probably take out some of the rebar in the process. We chose to do it differently. We actually bought what you're looking at here, these white rods. These are solid polyethylene rods, 3 inches in diameter and 8 inches long. You can actually buy these on eBay. There's a fellow on there that'll cut any length you want. So these are just screwed into the concrete forms. We just put some, I think they actually use drywall screws. Screw them in, and you can see they're screwed in at a specific height so that they line up. And then when the inside form goes on, there's just 2 screws through into each one of these plastic pegs from the inside. So they're secured into the forms, and the concrete pours around them. And this shows what the wall looks like after the forms have been stripped. And actually somebody has already tapped one of those rods out, but we found that they come out very, very easily. You just take a hammer and tap on them, and it's just like tapping a piston through a cylinder. They come right out, okay? The wall was poured with a aerial boom, just only practical way to get the concrete into the locations where these wall forms were. And here's our crew walking along. The lead guy's got the hose, the guy in the middle's got the vibrator, and then the guy in the back there, he's holding up the other end of the vibrator, and they basically walk those forms. I was very impressed with their balance. And then this is how easy it is to tap those out. Just take a hammer, tap on them, they slide right out, and you get a nice, clean, smooth hole. So each of these 8 holes has a single 1-inch tube coming through it, and we used a link seal. And I'll show you a photograph of the link seal that would give us a watertight seal between the wall and the tube. Okay, so here's the link seal. And there are other brands, but the basic idea is you've got a segmented rubber collar with stainless steel bolts and these plates, and you simply slide that in. It's like a donut. You slide it into the hole, you reach in there with your ratchet and just tighten up those bolts, and it squeezes the rubber nice and tight against both the outside diameter of the tube and the inside of that concrete hole, and you get a seal there that is rated for up to 20 PSI. Now, hopefully we'll never see anything even close to 20 PSI. against the outside of that wall. But you've got a good seal. And, you know, we've seen marginal installations where people have run polyethylene tubing through and then now empty a couple tubes of silicone caulk into the hole. Yeah, it'll seal it, hopefully for a while. It's not necessarily going to seal it like these do. So these give you a really solid seal. You can see these are the, we just trimmed off the excess, put some electrical tape over the end so we don't get bugs in there. And actually here we've got the 2 inches of foam insulation over the wall. We actually installed a floor drain right under where our manifold is going to be too. So far there hasn't been a drop of water that's really gone down through there, but if we ever did have to service it, it's nice to have a floor drain there. This shows the tubing coming through. Now, we also put 2-inch PVC sleeves in because we have a partitioned wall on the inside of this foam, a 3.5-inch 2x4 wall with mineral wool bats in it. And we don't want any condensation to get into those mineral wool bats. So we actually ran a 2-inch PVC sleeve right up to the link seal, ran the tubing through that, and then put some spray foam in there just to secure it. Right here, we've got a double band clamp going to a barbed adapter that goes right into a 1-inch ball valve. And then the ball valves come back. This is an 1.25 inch copper manifold. Got some ready rod here holding it up. And over here is where we actually filled and flushed the air out of it. We just put some steel fittings on there temporarily to adapt over to our flush cart. So that's what our internal manifold looks like. This has all been insulated. It's got 1/2-inch elastomeric foam insulation on it now. Here it is finished. You can see everything's insulated. The ball valves are all open. Here's our air dirt separator. Stainless steel pump, Armstrong circulator here. This is a compass circulator, I believe. Expansion tank. This is a service switch for the pump. We've got a pressure gauge on there so we can monitor that. And it is important to make sure that you get insulation on all this piping because that is going to run at temperatures that are well below the dew point of the interior air during the winter. And without the insulation, you're definitely going to get condensation. Okay. Just a close-up of the expansion tank. We use one of the hydroclaw brackets here. And we also have a piece of 3/8 rod here holding that 1/2-inch tube, just so when somebody eventually bumps into this tank, they're not going to bend it up here at the neck. And where the piping goes across the ceiling, we found these plastic connectors that go into channel strut. And what you can do with these, it's a little hard to see it here, but this insulation will actually slide right into the center point from both ends. And if you caulk that joint, now you've got a nice airtight joint, but you also have good structural support of the pipe. There's actually little arms that extend out from that outer plastic shell that hold this pipe mechanically. So the pipe is held there, but you slide the insulation in, you caulk it, and you've got a nice condensation-free joint. All right, we did our first poll question. Now what we're going to do is we're going to look at the other heat pump in the system here. This is a
so John, there's one question I just want to take care of since we're moving past it. Somebody had asked the question of how long roughly did it take you to do that earth lift?
About 5 hours.
The installation.
Oh, the insulation?
No, the actual earth loop itself. So you're saying it was about 5 hours?
5 hours. Yeah, it went fast. It went fast. That's we had basically 3 and at times 4 people down in the trench. We just followed the excavator right down the trench with the coils. So I'd say we had everything in and backfilled in about 5 hours. Okay, so air to water. Now, this was a test bed for a new heat pump that is, I believe it is on the market. It's available now from Space Pack. This is a low ambient air to water split system heat pump. This is capable of running to -22 Fahrenheit ambient temperature. So this thing can really hang in there at very cold temperatures. You can see the refrigeration line set right here. You've got a 3/8 line on liquid and a 5/8 line on suction. Outdoor unit, a little bit smaller than a monoblock. We put it on a stand, and that stand is actually anchored down to some pressure treated lumber that's down below grade. We put some landscape fabric down and some crushed stone just so we don't have weeds growing up underneath it. Obviously, we want to keep that unit up above the snow, so it's up about 15 inches above this crushed stone at this point. Piping wise, it just connects into the heat pump. It's piped in parallel with the geothermal water to water system. Okay. Here are the refrigeration connections before they're made up, and then you've got two 1-inch connections for copper tubing on the bottom, and on the outside, here's your 3/8 and your 5/8. These just got shipping caps in them to keep any contaminants out. So that's your service valves on that outside unit, and those are right here. There is wiring to the outdoor unit. Obviously, the compressor is in the outdoor unit here. And then there's the black cable you see, that's actually the control cable. That's control communication between the circuitry in the outdoor and the indoor units. Same story on performance. The warmer it is outside, the better the capacity of the heat pump. This heat pump can go up into the range of about, well, you can see here at 30 degrees outside, it's a 5-ton unit. It does have an inverter compressor. I can tell you this is a very quiet unit, definitely quieter than an on-off 5-ton or 4-ton scroll compressor would be. But COP, same story. The warmer, or I should say the higher the water temperature, the lower the COP. So we're running somewhere in this range right here. So we're seeing COPs, I would say midwinter COPs easily of about 2.5, maybe up to 3, depending on, again, water temperature and what the outdoor temperature is. So, you know, oftentimes we see geo, we see it sold based on very high coefficients of performance. Sometimes those coefficients of performance that you'll see in the literature are perhaps not attainable by actual field application of the unit. Don't base your decision completely on COP. You don't pay for COP, you pay for kilowatt hours. And what we're seeing on the air to water side of the industry, we're actually seeing those COPs improve significantly over where they were 20 years ago. As well as the ability for these machines to operate in cold weather. So the Canadian market is, you know, perfect example. These heat pumps are designed for cold weather applications, in some cases sub-0 degree Fahrenheit temperatures. So again, here's the two heat pumps tied into the buffer tank. Right now we are running this on a very simple, it's a little Tecmar 2-stage controller. And this is what we have. Our lead heat pump goes on when the buffer tank temperature sensor drops to 100 degrees, and it goes off at 110. And right now we are not using outdoor reset. We are simply using a set point control on it. And I'll tell you why in a minute. Our second, or our backup staged heat pump goes on if the buffer drops to 95, it goes off at 105. So we're averaging essentially about 105 in this buffer tank. Now, the reason we set it up with set point and not outdoor reset, we set it up for set point because we are also using this tank water to preheat domestic hot water, okay? And we've done some studies on this since the system was put in. We actually found the optimal performance is when we do use outdoor reset on the buffer tank, which would be a very simple control change in this system to do that. The trade-off that you get is this. The warmer you can keep the buffer tank, the higher the percentage of domestic water heating you're going to get. This is probably providing us with about 80 to 85% of the energy that we need for domestic hot water. But as we've talked about with the heat pump performance, the higher the buffer tank temperature, the lower the COPs. So where's that optimal point? How hot should I keep the tank so I can get a reasonable amount of domestic water heating, but not so hot that I'm penalizing performance of the heat pump? So again, we didn't know the optimal point when we put this in. We've done some spreadsheet modeling since then, and that's, I suppose, a story for another day, but we are getting good performance on both of these heat pumps at these relatively low temperatures. And you can see they both tie in right here. There's purging valves on the return side of the circuits. This is actually coming from the two heat pumps. This is going back and it splits up here, goes to the two heat pumps. We do have separate circulators. The circulator on our air to water was actually built in, so there's no circulator shown there. And definitely you want a check valve on each of these circuits, so if one is operating, the other is off, we don't get reverse flow. Okay. Now, controls, pretty straightforward. It's a Tecmar two-stage Tecmar 152 controller, fairly inexpensive controller. We've just basically got two relays that we can configure where these relay contacts close. Right now, our stage one, we're running between 95 and 105, and our stage two, we're running between 90. This shows 106 as the temperature shutting it off. Now, you might be wondering, what in the world is this thing right here? Well, it's this. It's a 4-pole double throw industrial switch. And all this does is it determines which is our lead heat pump and which is our lag heat pump. So with that switch in one position, the geothermal heat pump would take the lead. It would be on stage one, and the air to water would be on stage two. If we flip the switch to the other position, we're just flipping that order. And we do that, you know, for a number of reasons. We could get approximately equal run hours if we wanted to. I'm sure you could set something up equivalent to this that would flip it automatically. But being that this system was set up to test the performance of the air to water unit, we wanted the ability to easily make it the, you know, the main heat pump operating the system. And I've done some testing, and what we've found, interestingly, the only time that both heat pumps come on is when we throw on the garage circuit under cold conditions. So imagine a slab of concrete. The garage is 24 by 32 feet. It's a 4-inch slab. We let's say that slab sitting there at, you know, 35 degrees, and we turn that zone on. That's a huge load, transient load on the system, and that'll pull that buffer tank temperature down, and both heat pumps will come on. And under that condition, we've got about 8 tons of capacity, almost 100,000 BTUs per hour going into that buffer tank, and that will bring that temperature right back up again. So it's working well with this. The rest of this is just what we had to do to interface to the specific controls on these heat pumps. We used basically just some relays so that we could control how we wanted this unit to operate. It's a 2-stage water to water. And the way we want this thing to operate is we want it on high speed for heating and low speed for cooling. So to do that and coordinate with our other controls, we had to put a separate little relay in here. The two pumps that operate with the geo, this would be the earth loop pump, and this one would be between the heat pump and the buffer tank. Those are both operated directly from contacts inside the heat pump. Now, here's our spreadsheet model. I'm not going to bore you by, you know, going through all this, but here's what we found with the bottom line with this. This was actually based on the water heat pump. If we maintain the buffer tank between 100 and 110, and we ran this in our location, we used Syracuse, New York weather data, bin temperatures from Syracuse. We found that our seasonal average COP was 2.75. Now, here's one thing I found quite interesting on our model. When we lowered that buffer tank temperature just 5 degrees, so instead of 100 to 110, we're running from 95 to 105. Our seasonal COP jumped up to about 2.9. Just a 5-degree temperature change on that buffer tank had a pretty significant effect. And then finally, if we ran the buffer tank strictly based on outdoor reset control, our seasonal COP went up to almost 3.5. And now we're right up in the range where we're rivaling the COPs of a geothermal heat pump. So what I did is this spring, I compared our local prices here. Our price for propane is about $2.50 US dollars, obviously, for propane. Fuel oil was running at about $2.23 a gallon, and electricity we're paying about 9 cents a kilowatt hour. So with propane, delivered energy is about $29 per million BTUs. With fuel oil, about 18.5. With electricity and a COP of 2.75, we're at about a little under $10 per million BTUs, so significantly less than these two fuels. And if we were running with a full outdoor reset control on the buffer tank with almost a 3.5 COP, remember that's a seasonal average COP, we're actually running a little under $8 per million. So the takeaway here, we're finding that the energy delivered from this heat pump is actually, I would say, significantly lower cost per million BTUs compared to what's available to us for fossil fuels, propane or fuel oil. Where this house is built, there is no natural gas service. Another thing that we did when we modeled our performance, we did not allow the model to take the COP higher than 4.5. You have to be careful when you're doing modeling that sometimes, when you put continuous mathematical function together for things like heating capacity and COP, you don't want it to generate unrealistic numbers. And we felt that 4.5 was a reasonable upper end on COP. We also did not allow the capacity on that unit, which is a nominal 5-ton unit. We did not allow the capacity to be modeled over 68,000 BTUs per hour. So with those constraints, we're finding pretty good performance predictions based on, again, upstate New York weather. And that would be similar in weather to what you're seeing out there in southern Ontario. So these are all these different subsystems. What I did is I took the schematic that we had at the beginning of our session today, and I just pulled it apart into the subsystems. And this is a really good design exercise, I call it. You can treat these subsystems independently, especially when we use the buffer tank in a sense as our hub. Okay, essentially this system is as simple as operate the heat pumps to maintain the buffer tank at some temperature, and then draw from that buffer tank as needed for floor heating, for panel radiators, and what we're going to talk about next week for domestic hot water heating, and also for cooling. The heat pumps can chill that tank down for cooling, and we'll talk about that. I don't have time to talk about it today, but we'll talk about it in one of the other sessions. So those are all the pieces. There they are, put back together again. Here's just some more photographs. Okay, this is the hardwood flooring going down. You can see we used a mastic. We actually found it a lot faster after you look at this photo. Found it faster to put the mastic on the back of the floor as we put it down compared to putting it on the subfloor. Our makeup water, backflow preventer, pressure reducing valve, expansion tank that fit under a landing and the stairs. Here's our air and dirt separator. This is the heat exchanger that goes out to the glycol circuit in the garage. So that's got a separate expansion tank on it. Our control center, we've got a zone relay panel. Here's a couple Techmar controls, one for heating, one for cooling. Here's our master switch. Temporarily, I put our wiring here. This box right here has the relays and transformers that we use. So we gather all our, I'll say our small electrical components and tie them into a nice neat cabinet. This is actually domestic water down here. Here's our header. This is where all 4 load circuits, actually 5 load circuits, come back together. 1, 2, 3, 4, 5. We've got a purge valve on the end of that. And then our domestic water backup was a 30-gallon electric tank, went right under the stair landing. And we've got a thermostatic valve for anti-scald. And what we'll talk about next week, this little guy right here, this is a flow switch. This is what triggers our domestic water preheating subsystem. Okay. So Mike, we've got another poll question, I think, on air to water heat pumps at this point.
We do. So you guys should see the poll now. how many of your hydronic systems are likely to be air to water? I'll give everybody a minute to vote here. John, while everybody's voting, we had a question on why you use 25% propylene glycol and whether you used an autofill or a small feeder.
We use 25% glycol because the manufacturers usually recommend that as a minimum concentration so that the additives in the glycol are effective. In theory, a 20% probably would be okay, but the 25% was, again, based on the glycol manufacturer's minimum concentration recommendations. And I'm sorry, Mike, what was the other part of that?
Just whether you used a feeder or an autofill.
Oh, no. The water portion of the system, most of the system, other than the earth loop and the garage, is water. So we do have an auto feed system for water, for makeup water. But on the glycol, no, we do not. What we do, we like to oversize the expansion tank a little bit. And basically, we just pump some extra glycol into the expansion tank. And as our air vents are working, that extra glycol that is pressurized in the expansion tank will basically, automatically feed back into the system. So no, we did not use any auto feed on the glycol.
All right, so there's more people doing air to water than water to water, as we can see by the poll results.
I got a tiny little picture of that screen, Mike. What's that actually showing us?
So we're 5% of our participants are over 75%, 9% are 50 to 74, 13 are 24 to 60, and 48 are less than 25%, and 26% are not currently doing air to water.
Okay, well, it's a growth opportunity. Both geo, water to water, and air to water in particular, I think are two growth opportunities in North American market. As I said before, if you're doing hydronics and you plan to do it, 5 years from now, you really do want to understand heat pumps. I think the market is going to shift towards that. I'm not saying we're going to get rid of natural gas in 5 years, anything like that, but you are going to see more customers asking about all electric houses. And if you want to combine the comfort advantages of hydronics with the modern trending towards electrical energy and heat pumps, put it together with either geothermal or air to water, or both. I'm not saying pick one and just stay with it. I'm saying both of these are tools in your toolbox. We chose to put two in because we had a test heat pump to use. It's unlikely you're going to do a system that has both a geo and an air to water in it. It's possible, certainly, but it's unlikely. So you might have a lot where it's just impractical to do geo. If it's a fifth of an acre, you're not going to get a 25-ton excavator and dig up a fifth of an acre and put 4,000 feet of pipe in the ground. So an air to water would be a great solution there. If it's a big sprawling property, you've got no problems. Maybe you want to go with a geo. So, keep both of these products in mind because they're two more tools in your toolbox along with, obviously a wide spectrum of boilers. So let's go back to this. Next week, we are going to look at this subassembly right here. This is our domestic water preheating subassembly. So we're going to drill down into the details of how that works. So Mike, do we have any more questions? We're coming up on 9:30 here. Do we have any more questions?
We do. So we'll do a bit of housekeeping just for people that do want to jump off the call. We went a bit longer than we intended. Again, you've got the 5 handouts you can grab. Every week we're actually going to have slightly different handouts. PDF presentation will be available afterwards, and this is part 1 of 4. A recording of this presentation will also be made available afterwards for you guys. If you're not currently on our mailing list, definitely reach out and get on the mailing list. The next presentation after John and I are done is going to be with Robert Bean, and it's going to be on COVID and its implications on mechanical system design. So with that out of the way, I'm going to run through a bunch of questions here, John, for you that are going to cover a bunch of different topics.
Sure.
John had actually asked the question of what specs for the windows that were used in this house. What are the specs?
Well, they're all vinyl windows. They're triple glazed, so it's glass, and then I believe they use a transparent film for the middle layer, and then the inner layer is glass. They were a company called Paradigm Windows. They're made in Maine, in the States, and really nice, high quality, reasonably priced, low E coatings, and the R value on the glass was around 3.8. So that's
Okay.
what we used in the house.
Perfect. And then Ron actually wanted to know, since you use the same supply water temperature, did you account for temperature drop in your radiant loop runs, or was it insignificant?
Yeah. I haven't actually measured it, but we're looking at temperature drops probably in a range of about 15 degrees at design load on our radiant circuits, and across our radiators. Now, you don't have to have exactly the same temperature drop. Essentially, you focus on your supply water temperature. What we wanted to avoid is adding more mixing valves. You could say, we could look at running 120-degree water to the panel rads and then adding a mixing valve and going down to, say, 105 on the floor. Quite honestly, we try to avoid that extra hardware. So what we did is we simply put everything in, and we looked at supply water temperatures and found that they were close enough that we just piped them in parallel. We didn't use any type of mixing. The only mixing in this system is in the basement circuits. Those are low enough that we really wanted to put mixing in, because if we're, if we need, let's say, 85-degree water in the basement and we're giving it 105-degree water, what's going to happen? We're going to have a control problem. We're going to overshoot and undershoot with our thermostats. So that has a simple little, it's a Taco I-series mixing valve, works on outdoor reset control, but that's essentially the only mixing in the system.
Perfect. Chris had the question on your circulating pump, John. You want to know what your control strategy was, because you've got thermostatically controlled floors and radiators.
Yep.
Are you using constant pressure mode? If you can let Chris know what you did there.
Yep, great question. The way the system works is, as soon as they throw the master switch to heating mode, the circulator, it's a Taco 0018, very cool little circulator. It's actually got a Bluetooth connection built into it, and it has an app that goes on your phone. And we set that circulator up for constant differential pressure mode. And that goes on as soon as the mode switch goes to heat. It doesn't wait for a thermostat. So it's continuous circulation during the heating mode. And if all the thermostatic valves are closed, and if the thermostat that controls the grate room is closed, in other words, if there's no open flow path, the pump will go down to what I call a sleep mode at about 9 watts. And it'll just sit there and wait for something to open up. And it would be very similar to the small Velo, I think the EcoStratus Velo pump. Set it up for constant differential pressure mode, and it simply runs it runs 24 hours a day. I should say it's enabled 24 hours a day. The speed that it takes is simply based on how many flow paths are open. So as more radiator valves open up, the pump will automatically speed up to maintain a constant differential pressure. So it's a very, very simple setup. You flip the switch to heat mode, and the circulator goes on, and the heat pumps are enabled to keep the buffer tank warm.
Perfect. Joe would like to know if you used an HRV, John.
We did not use an HRV in this system. We do have exhaust fans in the kitchen and all the bathrooms, but there is no heat recovery on this. It was quite honestly, it was a budget decision. And the air quality is good in the house. They're actually monitoring it for radon, and everything is good. We haven't had any issues with condensation on windows. They do use the bathroom fans, and they use the kitchen fan, and that seems to be adequate for ventilation.
Darren would like to know, what is the hottest air temperature you can achieve at -22 on the air and water unit? This is a good one for you.
Yeah, he's probably thinking hottest water temperature. I honestly
sorry,
don't
water
know.
temperature. Yeah.
Yeah, I honestly don't know. It's a good question. I will tell you, -22 is a challenge. The COP of that heat pump is probably about 1.2 at that condition. I'd have to refer you to Space Pack to get the exact number on that. In our location, -22 is going to happen maybe 1 hour a year on a typical winter. So it's likely, if we know that kind of temperature is approaching, we'll flip the switch so the geo heat pump becomes the lead. That could be done automatically. If you wanted a little more control input, for example, you could enable the geothermal heat pump anytime the outside air temperature is below some setting, like pick 0 degrees Fahrenheit, and the system would automatically favor the geo heat pump then. We didn't go that route simply because we knew we'd be experimenting a little bit with this system, just set up with a manual switch. So I'd refer you to Space Pack to get what's the maximum water temperature at those extreme conditions.
Perfect. Daniel actually wants to know that plastic holder channel that you use for the HDPE on your geo install. What is the manufacturer?
Oh, I'm sorry. The classic what, Mike?
So the plastic struts that you use to hold the pipe in the building, he wants to know what that channel with the manufacturer is.
I don't know the manufacturer, but I can tell you we got them from supplyhouse.com. They have a listing for that. They're really nice. They're all plastic. They basically snap into the unistrut, and then you push the pipe up and snap them together. And as I say, structurally they hold the pipe, and they allow you to slide that insulation in. So I apologize. I don't recall the manufacturer, but they did come from. If you go to supplyhouse.com, they do have them available there.
Christopher actually has a really good question. He wants to know if you'd ever use an indoor reset control on a system designed with air to water or water to water equipment. Christopher, I can tell you I never have, but we certainly use outdoor reset. John, what are your thoughts on that?
Yeah, you could. The basic idea would be don't heat the buffer tank any warmer than necessary for whatever the conditions are. So I could see you configuring an indoor reset control and simply maintaining a buffer tank based on how the feedback from the interior space temperature is going. Yeah, I don't have experience in doing that, but I don't see any reason why it couldn't be done. I'm not sure which would be better for you. I suppose the indoor one does account for things like solar gain and other internal heat gains, and might give you a slightly lower water temperature requirement.
Okay. Robert actually asks a very good question. So he's just pointing out this is a pretty complicated system, and he's wondering how difficult or expensive it is for the homeowner to maintain it. Before you answer that, John, I will just point out that obviously we sell a lot of heat pumps and we design a lot of systems. A lot of the controls that John showed you that appear to be quite complicated is actually packaged in the equipment. So really, you've got a packaged heat pump, you've got a buffer tank and peripheral piping, just like you would on any other hydronic system. It just requires a higher degree of training to understand what you can and can't do with a heat pump versus a boiler. John, what would you add to that, Steve?
Yeah, the maintenance really hasn't been bad at all. I mean, I would say we really haven't had any problems. One of the things that we did do in this house, because we're in a rural area and our power quality out here isn't always the best, we did put a whole house surge suppressor on the main entrance because we don't, any electronics are susceptible to, get a nearby lightning strike or something like that. We didn't want any damaging voltage spikes to going to these electronic controls. But maintenance of the system really, you put it in, you purge it. We really haven't had any issues here beyond what we would have with any hydronic system. Good air separation. I did check the water. I did check the dirt separator this spring, and the water was nice and clean. So again, the maintenance hasn't really been a problem. The thing I would stress with the heat pump, again, low water temperatures, simply run the heat pump at less stressful levels. If we run the heat pump, if we're trying to get 130-degree water and it's 10 below zero outside, it may be possible for the heat pump to do that, the air to water, but you're running this thing at some pretty high compression ratios. And like any mechanical device, the harder you run that, the longer or the shorter its service life is going to be. So, from a maintenance standpoint, we really haven't had any issues with this.
Yeah, the big takeaway from that is that at 130 degrees, you're actually at the upper envelope of what that compressor will tolerate from a refrigerant pressure standpoint.
Yeah.
But it's a good question. The systems look complicated because we break them down quite a bit, but it's actually very easy to accomplish.
Yeah, and I'll point out too, Mike, that if, for example, if you didn't want to heat the garage, we could take away that whole subsystem. If you didn't want to heat or preheat domestic water, we could take away the system we're going to talk about next week. So we could take this system and pare it down to, a much simpler setup where, we're doing a lot of different things, and we wanted to show you this system, not from the standpoint of look at how complicated it could be, but we wanted to show you the versatility that is possible with hydronics. So if you wanted a simpler system, for example, maybe you don't want cooling. You could eliminate the air handler, eliminate anything to do with the chill water side of the system. You could just set it up and just do floor heating. And if it was a high mass single zone system, you probably wouldn't even need a buffer tank. You would have a hydraulic separator between the heat pump and the floor and just turn the heat pump on and off based on a thermostat. So, I don't want to leave the impression that if you're working with either a geo water to water heat pump or an air to water, it has to be a sophisticated system. It can be a very, very simple system. It's just a matter of what are you trying to accomplish with that system.
John, another question is, did you consider doing tankless from a domestic heating standpoint?
We considered it. It would have been an electric tankless unit, and we do have a 200 amp service panel, so we could run it, but we chose to go with the 30-gallon tank. It was simple. It's got a 4,500 watt element in it. So if our preheating subassembly for any reason isn't preheating our domestic water, for example, if we just shut off this system completely, we still got a 4,500 watt element in a 30-gallon tank. And the water use in this house is pretty conservative. 2 gallon per minute shower heads and so forth. So we decided the other issue with a whole house electric tank, if you get up in a range of maybe 30 kW on those heaters, that's a very high amp draw. And quite honestly, you probably find you're spending more to wire the thing than you spent to buy it, because some of those require at least two, maybe 100 watt breakers, double pole breakers, when you get up into a whole house size unit. So we just got a single double pole 30 amp breaker servicing a 4,500 watt element in 30-gallon tank, and that easily handles the whole system. At some point, I've told my son-in-law to experiment, but not to tell my daughter about this. I said, just turn the breaker off on that electric tank and go for a week and see if you get any complaints. So at some point, he's going to get brave and do that.
So here's a twofold one. I'm going to combine two questions from Mike and Clement into one. So the first part is, are the remote TRVs hidden in any way, like under the floor? And then Clement's adding to that, has your son-in-law and daughter had to adjust the TRVs, like as the seasons change, or they've been pretty happy from a comfort standpoint?
They've been pretty happy. You know, they will turn them up when it's cold a little bit, turn them down just like you would a thermostat. As far as accessibility, you have the knob where you do the adjusting, and then you have a 2-meter long capillary tube that goes down. And what we did, the two valves are actually down in between the floor framing. And we have, one of them is where the floor framing is open, and it's just a matter of going to it. If you ever have to get to it, it's right there. The other one is actually above a drywall ceiling, and we put in a 12-inch square excess panel right below the valve. If we ever have to get to that valve, we just pop the excess panel and the valve's right there. But quite honestly, there really shouldn't be a need to have to get to that valve. You know, like anything, if it ever does fail, we do not want to bury a valve and forget about where it is, obviously. So simple little access panel and a drywall ceiling takes care of that. I do want to share a story. My grandson, when he was 2 years old, did discover how to turn valves on radiators. And I got a call one day that one of the remember, there's 2 radiators in the living room. And my son-in-law called and says, one of them is cold, the other one is warm. So I went over there and I found that even though it didn't have a TRV on it, it still has that little plastic cap that comes with it that covers the little valve that's built into the top of the radiator. And my 2-year-old grandson discovered how to turn that all the way to the closed position, and didn't tell his parents about it. So kids will play with that stuff until you instruct them otherwise.
That's why I was always hiding screwdrivers, John. My little guys were good at it as well.
Yeah.
We have quite a few more questions. Do you want to go through the next couple of slides? Because you're going to show some pretty cool stuff on what you think might work and won't, and then I'll get back to the rest of these questions afterwards.
Yeah, I'll show you real quick. What we want to do with all these webinars is at the end, we just want to build in what we call find a fix. And all we're going to do is we're going to look at an error in a piping system and identify what's wrong with it and show you how to fix it. So one of the errors that we've seen a lot of is this piping right here, where somebody is trying to mix what they think of as a primary loop with what they also think of as a header system. So you see that the piping here essentially shows a loop. And I put quotes around primary loop and primary circulator here. So we've got this loop, but instead of closely spaced T's, their idea is we'll do all our takeoffs up here where the water is warmest, and then we'll do our returns down here where the water, obviously with the water coming back from the loads, is going to be cooler. And this is an undefined piping assembly. This is not a header system, and it's definitely not a primary secondary system. And you can get into problems with this, okay? And the problem you're going to get into is when the primary circulator is on, and assuming that you built this, you would probably wire it so that the primary circulator would be on anytime any zone calls for heat. What's going to happen is you're going to get some flow in not only the zone that has its zone circulator running, but you're going to get flow in the other zones as well. Not as much, but you're going to get what I'll call heat migration, or the term that our industry loves is ghost flow. And it's happening because of the pressure drop between these T's up here, between where the water leaves and where it comes back, okay? And depending on the flow rate of the zone circulators versus the primary circulator, you're going to get flow reversal. And I just want to show you, this is another way to look at it. This, again, is an undefined piping assembly. It's not primary, secondary. Somebody does this because they think, I'm going to take all my supply water at the highest temperature, leaving the boiler, send it to my loads, and then I'll just collect the returns downstream of that. Okay? So let me show you what's going to happen. let's say we've got 3 zones and one zone is off, one zone's running at 10 GPM and one's at 4. Okay, so our total flow going out to our loads is 14 gallons a minute. And let's just say we've got 15 gallons a minute in our primary circuit. Under those conditions, not a problem. Okay, because if we've got 15 here and 14 leaves, that leaves 1 gallon per minute to flow through and so forth. We aren't getting any flow reversal. We aren't getting any mixing. The question is, how do you guarantee that this flow rate is always going to be greater than the total of these 3 flow rates? I suppose you could put a massive pump on there to do it, but you know, that's really not good design. So let me show you what happens now if our primary circulator only produces 8 gallons a minute, but our load circuits are still a total of 14. Well, what's going to happen is we've got 8 gallons a minute here. So 8 gallons a minute has to leave downstream. We've got 14 going up here, 14 coming back. The only possibility right here between the supply side and return side is 6 gallons a minute of flow reversal. So we're going to start to get mixing, which is going to reduce our water temperature down. You know, this mixing effect is definitely going to dilute our supply water temperature. And we've seen this quite a bit. So you don't want to do that. What you want to do, you have to decide, am I building a header system or am I building a primary secondary system? If it's primary secondary, the T's need to be close together, right next to each other as it shows here. Okay, so be careful about morphing or trying to take what you think might be the better parts of, you know, a primary secondary system versus a header system and trying to morph them together. Sometimes what you get is Frankenstein. So, oh, we had one last poll question too. Do we want to do that now, Mike?
Let's do that poll. So the last poll that we had is whether or not you guys are using buffer tanks in your hydronic systems where you have multiple zones.
And maybe we can do a quick question while the poll results are coming in too.
Yeah, Jeff would actually like your feedback on heat pump water heaters and whether you considered it for this this project for your daughter and son-in-law.
Yeah, we did not consider heat pump water heater here. They're a fine product when you've got a scenario where you've got excess heat available inside the building. But when you're heating the building with a heat pump, and then you're using a heat pump water heater, you've got 2 heat pumps in series. It'll work, but remember, a heat pump water heater is going to cool that interior space. So I see them more, quite honestly, more practical in situations where you've got excess of heat. It might be a commercial application. Maybe you've got a sunroom or something where you get, you know, nice excess heat when the sun is out. But to just use it as a routine water heater when the building itself is being heated with a heat pump, or for that matter, with any other fuel. If you look at the overall thermodynamics, you essentially have a heat pump in series with whatever is heating the building. So your net effect is not as great. I think they're fantastic products in the right applications. Obviously down south where you've got unconditioned spaces that have plenty of low-grade heat available, like a basement, a fantastic product for that. But no, we did not consider it here.
Yeah, so this is interesting results. So 31% are always, 39% are sometimes, 22% not very often, 9% never. Since we're talking about air to water and water to water, you could, in a boiler application, depending on modulation, say you don't need a buffer tank. In air to water, water to water, there are very, very limited applications where you're not going to have a buffer tank because they just don't have that modulation level. So
yeah, some of the one unit that we did use here, the air to water, does have an inverter compressor. In theory, it can go down to about 30% of its rated capacity, roughly about 2 tons. One nice thing about that In heating, we've got a lot of zoning. You saw we had 5 thermostatic zones, and we had one with an electric thermostat, plus the basement and plus the garage. So we actually had 7 independently controlled zones on heating. Definitely want a buffer tank on something like that. On cooling, we only had 1 zone, the whole house. And one of the nice things about an inverter compressor is that you can set the temperature you want that heat pump to produce in the chill water mode. Let's say we set it for 45 degrees Fahrenheit. It will actually ramp that compressor down to maintain that. So in cooling, in theory, we could eliminate having to chill the buffer tank down in cooling with an inverter compressor. We're using the Geo heat pump for cooling, and the reason we're doing that is we have a desuperheater in the Geo heat pump, and the desuperheater is essentially free domestic water heating when you're in cooling mode. The air-to-water unit that we use did not have a desuperheater. You do have a Canadian heat pump manufacturer, Nordic, that does offer a split system air-to-water that does have the option to have a desuperheater in it. And that's nice because, again, when you're running a heat pump and cooling operation, instead of just rejecting all the heat outside, you're using some of that heat to at least preheat to a pretty, the preheat percentage. Obviously, it depends on water temperature and usage patterns, but I wouldn't say that 75% of your domestic water heating is coming from your heat pump out of that desuperheater when you're operating in a cooling operation. Okay. Mike, what do we want to do next? We could either do questions or we can do one more find a fix. I don't want it to run too long.
Sure, let's do the other find the fix, and I'll go through the questions and pick out a few good ones, and then we'll wrap up.
Okay. Let's go back here then. All right, so the last find the fix here would be a system that lacks boiler protection. Now we're talking about conventional boilers in this. We're not talking about mod cons here. So if you're working with cast iron, steel fire tube, or copper water tube boilers, those boilers are not designed to operate with sustained flue gas condensation. So if we create this schematic that you see here with the big X across it, we've got a 3-way thermostatic valve, so we're controlling our supply water temperature, but notice what's going back to the boiler is it's not boosted at all, and we're going to create sustained flue gas condensation in the boiler. I can tell you from experience, when the radiant industry first started to kind of rejuvenate back in the 1980s, this was occurring every day. There were disasters, particular with cast iron boilers, because the industry simply didn't understand how important it was to protect the boiler against temperatures that were below the dew point of the water vapor and exhaust gas. So we definitely have to put some kind of boiler protection in. You can do it with a second 3-way thermostatic valve if you want. This valve here is going to boost the water temperature going back to the boiler. I'll be honest with you, this technically is possible. I wouldn't recommend it as my first choice. I would go with this, a 3-way motorized valve that has a boiler return sensor on the controller. And the way that's going to work is that sensor on the boiler return down here, when that drops below some set point, 130 is typical, it's going to start to close down the hot port in this mixing valve. In other words, it's not going to sacrifice the boiler by allowing it to operate with sustained flue gas condensation. It's going to instead limit the supply water temperature until the boiler gets up to the proper operating condition. And if you've sized the boiler to meet the floor heating load, it will get there. It's just a matter of taking some time. If you have a cold slab that you're starting up, what this detail does is it prevents flue gas condensation during that transient period. So I would stress to anytime you're using a conventional boiler in either a new system or a retrofit. Now, let me give you a scenario that you may not think about. You could go into a building that has a high temperature hydronic distribution system and say, I'm going to retrofit this building with a heat pump. And as part of that retrofit, I'm going to add more heat emitters to the system, okay? And in doing so, maybe you can bring that supply water temperature down to, say, 120 degrees at design load, all right? You can also bring water temperatures down by increasing insulation in the building, or changing to better windows, or reducing air infiltration. In other words, anything that brings the load down would bring down the required supply water temperature. So let's say you've done that, and maybe that building had a conventional boiler in it, and it's worked fine for years, no flue gas condensation problems, and all of a sudden now you've remodeled the distribution system for low water temperature. Well, don't forget to go back and add boiler protection. If you're going to keep that original boiler as part of the system, put an anti-condensation mixing valve on it. And several companies have those. Calefi has those, and some other companies. And all they do is they elevate the boiler temperature so it doesn't operate with sustained flue gas condensation, but they also allow you to use a mixing valve. So you could run your floor circuits way down to, in theory, you could run the water temperature to the floor circuits right down to what the room temperature is, and still have the boiler operating high enough that it doesn't operate with sustained flue gas condensation. Okay, let's go back to some questions, Mike.
Yeah, so Dan had asked the question if you considered a VRF-based system instead of the water-based.
No. VRF meaning multiple indoor units with outdoor condenser unit, or what, in a residential application, usually you consider it sometimes call it a ductless mini split, a multi-head ductless mini split. We didn't. I'll be very honest with you. Hydronics beats those from a comfort standpoint every day. The comfort aspect of properly done hydronic heating is unmatched with any type of air-based system. So again, VRF systems and ductless mini splits, they're doing well in the market right now. They're fairly simple plug and play. But in my opinion, they do not match the comfort of floor heating or panel radiators. So where comfort is the priority, hydronics is the choice.
Yeah, and my friend Mr. House has the question, what would the cost be if we were to do this system with a high efficiency gas boiler versus what we've done here? And I'm assuming he's either looking at installation or operating costs.
Yeah. The cost would be lower, I'm sure. The boiler would replace,
installation cost, yeah.
Yeah, we've got two heat pumps here. One of them was part of a test system, so that was a system that the manufacturer gave us to test it. But the other thing that did have weight in this decision in the United States right now, we had. Well, last year when this was put in, we had a 30% federal tax credit on the geo system. And within New York State, we had an additional $1,500 per ton rebate on geo. And honestly, between the two of them, that brought the cost down substantially. Without those rebates, I'm sure that the gas, if you had natural gas service available, and again, we don't, this house was in a rural area, I'm sure the cost of installing and probably of operating would be, the operating cost would probably be similar. The installation cost would definitely be lower. So
yeah, so interestingly, on the operating cost, Jeff and everyone else, you can actually download the case study that I have attached as a handout, which is the field study that Enbridge did. Again, this week's is the cooling data. Next week's will be the heating data. We, in our company at Eden Energy, we actually do the calculation based on BTUs per dollar. You have the installation cost, but then it's how many BTUs per dollar am I going to get over the lifespan of that unit.
Yeah, and you know, if you go back and if you download these slides and take a look, we did compare what our other options were, our propane option and our fuel oil option. And we actually, I mentioned another project that we modeled, and this was in a house in Boston, a little warmer. Their design temperature was 9 degrees Fahrenheit. We actually found that the cost of operating the air to water heat pump on $1 per million BTU basis was slightly lower than the cost of natural gas. And keep this in mind too, when you do have natural gas available, obviously you have to have the meter on the house, and there is a monthly service charge associated with that meter. And I think in the Boston area, it was running around $18 a month just to have the meter. So as house heating loads get smaller, you have to ask the question, am I using enough natural gas to justify $18 a month just to have the gas meter on the house? You know, it's conceivable that that basic service charge for the gas meter is going to be a significant part of the bill if the house is using minimal amount of natural gas. That basic service charge does not go down based on usage. So again, the trend that I'm seeing in North America is a trend towards all electric buildings, which would eliminate the gas meter and save you the $18 a month, besides having, I'll say, a competitive cost of energy on $1 per million BTU basis, the heat pump versus the natural gas.
Yeah, and on that note, John, Clement asked the question, when you were doing your metering, did you use standalone meters when you were comparing the ground source and the air to water to calculate COPs, or was it just measuring operating hours?
No, we simulated COPs using the manufacturer's curves. Those graphs that I showed, and they're on the PDF, those are the manufacturer's rated curves for heating capacity and for COP. So we didn't actually set up instrumentation, at least at this point, we have not set up instrumentation. I don't own the instrumentation to set it up, but we did simulate the performance based on the manufacturer's performance curves, and we combined that with the water temperatures that the system requires, and also we combine it with the climate data. The closest available climate data for this application was Syracuse climate data.
Chris John has noted that your ground loops are quite long, and he's wondering if that was a conscious part of your design to keep entering water temperature higher throughout the heating season.
Well, they're about 950 feet with 1-inch pipe. We did do the flow calculations. That's not, the pump that is on there, it's an Armstrong Compass, I believe it's the Compass R. It's the larger Compass circulator. That circulator does have a wattage readout on it. And we're running at about 147 watts pumping the earth loop. We looked at the Reynolds numbers. We looked at, are we going to ensure that we have turbulent flow? We even looked at 3/4 inch pipe, but to answer his question, 1,000-foot coils are available. They are heavy. I can tell you, when you walk those coils out, you gotta unroll the coil, never pull it off the side of the coil. But no, the 950-foot long circuits, 4 of them in parallel with that pump, we had no problems as far as flow rates. And as I say, we're operating that entire loop at 147 watts of pumping input power.
And then David wants to know on the air to water installation, why was the heat pump installed on the north side of the house?
Because that's where our line set allow us to do it. And we did look at the south side. We were going to have to use a longer line set, and just where the windows were and so forth, we decided to put it on the north side of the house. Aesthetically, it's a little better there too. So it's a good point. If you can put it where it's going to have more sun on it, And assuming that that's okay with the clients aesthetically and so forth, you probably will have a slight advantage if you have a little microclimate, I guess I'd call it, around that air-to-water heat pump. But with the performance that heat pump can generate, the difference between north side, south side, and keep in mind too, on the north side, we only had about 10 feet of line set. And the length of the line set will have some effect on performance. The longer the line sets, the COPs and capacity do go down a little bit because of just more friction that the compressor, you're going to have a lower refrigerant flow rate with a longer line set.
Perfect. And then Terry actually has a good question about domestic hot water. He wants to know why there was no provision for it. I'll just point out that on water-to-water heat pumps, you can get domestic hot water built into many units, including the water furnace unit. And depending on how many people are living in that space, it'll produce about 50% of your annual domestic load. Keep in mind, that's an annual number, not a daily number. It's not producing hot water under all conditions. Is there a reason that you didn't have it, John?
Oh, it's there. The Geo water to water does have a de-superheater on it, and we're using that. Whenever that Geo heat pump is running, that de-superheater is circulating between that 30-gallon tank and the heat pump. And then I would say tune in next week because we're going to show you how we use the buffer tank to preheat the domestic water. So we actually have 3 inputs for heat on domestic water. We have, if we need it, we've got a 4,500 watt element in the 30-gallon tank. We also have the de-superheater built into the water-to-water heat pump. And we have a what we call a sidearm heat exchanger that, again, we're going to talk about in detail next week, that will use the energy in the buffer tank through a stainless steel brace plate heat exchanger to preheat the water. So I would contend that we could probably shut off that breaker to that 4,500 watt element, especially in the summer when that heat pump is running and cooling, and get the majority of our domestic hot water. The 4,500 watt element is simply there as a backup. If the output from the de-superheater and the preheating that we're getting from the buffer tank are not sufficient, the 4,500 watt element, I forget what the tank temperature is set to. It's not very high. It's probably 120, 125 degrees on the thermostat. But we're definitely using the heat pumps for domestic water heating here.
Perfect. Well, it's now 10 after 10, so I think, John, at that point, I'm going to wrap it up. I'll note that there's a small handful of questions we didn't get to now. We'll be back again next Monday where we're going to be talking about domestic hot water, preheat systems without and heat exchangers without doing traditional methods. If any questions come up between now and then, obviously everybody has my email address. Feel free to send an email. John, thank you for doing this today, and obviously we look forward to doing it again next week.
Yeah, and one final thanks to our sponsors. Again, thanks for helping us keep this education outreach going during our, as I call it, our COVID era.
Yeah, if anybody's working on interesting projects, definitely reach out to me. I can tell you that all of these sponsors are looking to do case studies involving their product. Coletti and IBC in particular are looking to do up some really nice case studies. If you're working on a project and think it might be a good fit, you can send me an email. If you have any questions or feedback on that or other items, there's the 800 phone number in the bottom right-hand corner. Otherwise, that's all from me, and thank you, John. We appreciate you doing this for us.
Yeah, thank you, Mike, and thanks, folks, for tuning in. We'll see you next week. We'll keep going.
Thanks, folks. We'll see you next week.